Pluto is a crime scene, not a metaphor, not a dramatic flourish, a genuine crime scene where the evidence contradicts the official story, where every new piece of data rewrites what came before it, and where the perpetrator, the universe itself, has left behind clues we're only now learning how to read. For 76 years, we called it a planet. We put it in textbooks. We hung it on classroom walls. We gave it a proud spot at the end of every solar system model sold in every toy store in America, right there after Neptune, the smallest and coldest and most distant member of the family. Children memorized it. Teachers taught it. Scientists accepted it. And for most of those 76 years, almost nobody thought very hard about what Pluto actually was, because the answer seemed obvious: a frozen rock, a distant relic, a cosmic footnote. Then in 2006, the International Astronomical Union voted to strip that title away, and most people stopped paying attention entirely. They figured the story was over. A small, frozen rock at the edge of the solar system, demoted and forgotten, not even worth the argument anymore. That is the version of Pluto most people still carry in their heads today. A placeholder, a punchline, a cautionary tale about the impermanence of scientific categories, and almost none of it is true. Because while we were busy arguing about what to call it, Pluto was busy being one of the most geologically violent, chemically complex, and scientifically confusing objects we have ever encountered in the entire solar system. It was running active geological processes. It was cycling an atmosphere on a 248-year schedule. It was building mountains out of frozen water harder than granite. It was carving glacial valleys with rivers of solid nitrogen. It was possibly hiding a liquid ocean beneath its surface that has existed, undisturbed and unseen, for longer than complex life has existed on Earth. And when the New Horizons spacecraft finally arrived in 2015, after a 9.5-year journey across the solar system, what it found didn't just surprise scientists. It broke their models. It shattered the assumptions. It forced a fundamental rethinking not just of Pluto, but of an entire class of objects we had collectively decided to ignore. This is what Pluto actually is, and why it matters more than almost anything else we've discovered in the outer solar system. The distance problem. The first thing you need to understand about Pluto is where it lives, because the distance alone is almost incomprehensible, even by solar system standards. Pluto orbits the Sun at an average distance of about 5.9 billion kilometers. Let that number settle for a moment. Not million, billion, 5.9 billion kilometers. That is roughly 39 times farther from the Sun than Earth. If you drove a car at highway speed, 100 kilometers per hour, without stopping, without refueling, without sleeping, it would take you approximately 6,700 years to reach Pluto. The Apollo astronauts made it to the Moon in about 3 days. Pluto would take them 12,000 years at the same speed. At that distance, sunlight is about 900 times dimmer than what you feel standing outside on a clear summer afternoon. Noon on Pluto looks like deep twilight here on Earth, the kind of twilight where you can barely read, the kind of twilight that feels like the world is shutting down for the night. Except on Pluto, that is always what it looks like. There is no brighter moment. The Sun from Pluto's surface is just a slightly brighter star, an intense, blazing point of light that illuminates almost nothing. The temperature at the surface sits around -230 degrees Celsius. Let's be precise about what that means, because numbers this extreme lose their impact if you just glance past them. -230 degrees Celsius is cold enough to freeze nitrogen solid, not into a liquid, solid. The same nitrogen that makes up 78% of Earth's atmosphere, the invisible gas you breathe right now. On Pluto's surface, it is rock. Hard, crystalline, frozen rock. The air itself becomes stone. For decades, every model we had said the same thing. At that temperature, at that distance, with a body that small, roughly 2,377 kilometers across, smaller than Earth's moon, smaller than a dozen moons in our own solar system, Pluto should be dead, geologically inert, a frozen ball of ice and rock with nothing happening on its surface, nothing happening underneath, and nothing interesting to say. The scientific consensus going into 2015 was unanimous and confident. Pluto was a relic, a leftover chunk of debris from the formation of the solar system, sitting in the dark, doing nothing, going nowhere, becoming nothing. That consensus was about to be demolished. The Arrival New Horizons launched in January 2006, ironically, the same year Pluto lost its planetary status. The spacecraft was built around a single objective: get to Pluto and get close, not orbit it, not land on it, just fly by it fast enough to escape the sun's gravity and continue outward, and in those few hours of close approach, gather everything possible. New Horizons arrived on July 14, 2015. After a 9.5-year flight, it passed within 12,500 kilometers of Pluto's surface at a speed of about 49,600 kilometers per hour, roughly 14 kilometers every second. The encounter lasted only a few hours. There was no slowing down, no orbiting, no second pass. The spacecraft had one shot, one window, one irreplaceable opportunity to collect as much data as possible, and then it was gone, flying onward into interstellar space. Think about what that means for the engineers and scientists involved. 14 years of work, proposal, design, construction, launch, cruise, culminating in a few hours of frantic data collection as the spacecraft hurtled past at incomprehensible speed. Everything had to work. Every instrument had to function. Every byte of data had to be captured and stored correctly, because there was no going back. And then, even after the flyby, the wait continued. At that distance, transmitting data back to Earth at the speed of light still takes about 4.5 hours each way. The download rate was painfully slow by modern standards, a few kilobits per second. Over the next 15 months, New Horizons transmitted everything it had gathered back to Earth, piece by piece, image by image, measurement by measurement, and piece by piece, the old version of Pluto fell apart. Sputnik Planitia, the heart of a dead world that isn't dead. The first image that stopped people cold was of a feature now called Sputnik Planitia. It is an enormous plain of nitrogen ice sitting inside what appears to be an ancient impact basin on Pluto's surface, roughly 1,200 kilometers across. From a distance it looked smooth, almost featureless, eerily flat. That alone was strange, because a surface that smooth in a place that old meant something was actively erasing craters. This is a critical point. In the solar system, small, cold bodies accumulate impact scars over billions of years. They don't have the geological activity to fill craters in, smooth them over, or otherwise erase the record of past impacts. Bodies like Pluto were supposed to be archaeological records, surfaces frozen in time for 4 billion years, every crater still precisely where it was left by an ancient collision. Sputnik Planitia had almost none. The surface appeared to be less than 10 million years old. In a solar system that is 4.5 billion years old, 10 million years ago is essentially this morning. On geological timescales, that's yesterday. Something was actively resurfacing this region, wiping away the craters, smoothing over the evidence, making Pluto's largest basin look younger than the age of the dinosaurs. When the high-resolution images came back, the smoothness turned out to be an illusion of a different kind. The plain wasn't flat. It was divided into irregular polygonal cells, each one roughly 10 to 40 kilometers wide, separated by shallow troughs. They looked, and this comparison appeared in actual scientific papers, like the cracks on top of a cooling pot of oatmeal, or the surface pattern of a lava lamp, or cracked mudflats seen from altitude. That comparison turned out to be closer to reality than anyone expected. The cells are convection patterns. The nitrogen ice in Sputnik Planitia is slowly churning. Warmer ice from below rises to the center of each cell, spreads outward as it reaches the surface, cools, and sinks back down along the edges at the troughs. The entire plane is turning itself over like a lava lamp running in extreme slow motion, completing one full overturn cycle roughly every 500,000 years. On a world that was supposed to be frozen absolutely solid, the ice is moving. Continuously. Actively. That raised an obvious question, one that nobody had a clean answer for. Where is the heat coming from? Pluto has no tidal heating. It's not being squeezed and flexed by a giant planet's gravitational pull, the way Europa or Enceladus are. Those moons orbit massive Jupiter and Saturn, respectively, and the continuous tidal stress generates substantial interior heat. Pluto has no significant source of external energy. The sun is barely a bright star from its surface. It certainly isn't delivering meaningful heat. The only explanation that fits the data is internal heat, specifically residual energy from radioactive decay in Pluto's rocky core. Certain heavy elements, like uranium, thorium, and potassium, release heat as they undergo radioactive decay over billions of years. Large planets retain this heat well because of their mass. Small bodies lose it quickly to space. The math for Pluto, given its size, says it should have radiated away essentially all of its internal heat long ago, billions of years ago. And yet the convection was right there in the images, undeniable, operating, doing something that the math said shouldn't be possible. Nobody has fully resolved this contradiction. Several hypotheses have been proposed. Perhaps Pluto's composition is slightly different from what models assumed. Perhaps the insulating properties of nitrogen ice are better than expected. Perhaps there are additional heat sources that haven't been accounted for. But as of the most recent literature, including papers published through 2024, there is no complete, universally accepted explanation for why Pluto's interior is still warm enough to drive the convection we can clearly see. The data is right, the math is wrong, and we don't know why. The mountains that shouldn't exist. The geology didn't stop at Sputnik Planitia. As New Horizons images came back, scientists cataloged an increasingly impossible landscape. Mountain ranges made of water ice, some of them rising 3,500 meters above the surrounding terrain, nearly the height of the Alps. This needs context. Water ice on Pluto isn't soft or slippery the way you might imagine. At -230 degrees Celsius, water ice is approximately as hard and rigid as granite is on Earth. It doesn't flow. It doesn't deform. It behaves mechanically like rock. So when scientists say there are water ice mountains on Pluto, they mean there are mountains, real, solid, imposing mountains, made of a material that is technically water, but functionally stone. These weren't eroded stubs either. They had sharp edges, clean faces, the kind of angular, fresh features that suggest recent formation, possibly within the last 100 million years. On a 4.5 billion-year-old body, 100 million years is recent. Something pushed those mountains up. Something was still building terrain on a world that every model said should have gone geologically quiet 4 billion years ago. And then there were the glaciers. Not water ice glaciers, nitrogen ice glaciers. Pluto has flowing rivers of frozen nitrogen that creep down from the highlands and pool into Sputnik Planitia, the same way glaciers on Earth flow down mountain valleys and pool into lowland basins. They move imperceptibly slowly by any human standard, but they move. They carve channels. They leave flow marks preserved in the ice. They deposit material. They reshape the terrain. On a world where the temperature never climbs above -220 degrees Celsius, where the atmosphere is 100,000 times thinner than Earth's, where the sun is barely a bright star. On that world, there are active glacial systems reshaping the landscape right now. I want you to sit with that for a moment. We have trouble keeping roads intact through a single winter in the Midwest. Bridge foundations crack, pipes burst, infrastructure erodes, and we're doing this with a thick atmosphere, a warm sun, liquid water doing all the mechanical work. Pluto is running an active geological resurfacing program. Mountains, glaciers, convecting plains, at temperatures that would freeze oxygen into a solid block, powered by heat sources we can barely measure, in an atmosphere so thin it barely counts as one. The Kuiper Belt Revision. To understand why all of this matters beyond Pluto itself, you have to understand where Pluto came from. It is a Kuiper Belt object, one of potentially hundreds of thousands of icy worlds drifting in a vast ring of debris beyond Neptune's orbit. The Kuiper Belt stretches from about 30 to 50 astronomical units from the Sun, a region so vast and so dark that for most of the history of planetary science, it was effectively invisible. We knew it existed mostly because Neptune's orbit behaved in ways that suggested gravitational influences from beyond. The actual population of objects only became detectable as telescope technology improved in the 1990s and 2000s. For most of that history, everything in the Kuiper Belt was assumed to be inert, cold, dead, and uniform. Just rubble left over from the solar system's construction, too small and too cold to do anything interesting. Pluto was supposed to be the largest piece of that rubble, nothing more. The New Horizons data demolished that assumption so thoroughly that it forced a rethinking of the entire outer solar system. If the biggest known object in the Kuiper Belt turned out to be this complex, this active, this geologically alive, this chemically rich, what about the rest? What about Eris, which is roughly the same size as Pluto and orbits even farther out, in an elliptical orbit that takes it nearly 3 times farther from the Sun than Pluto at its most distant? What about Makemake, or Haumea, a strange, rapidly rotating object shaped like an American football, or distant Sedna, sitting out at the fringes of the solar system in an orbit that takes 11,400 years to complete? We have almost no close-up data on any of them. We've been assuming they're boring because we've never bothered to look. The New Horizons mission proved that assumption is dangerous. Pluto was, by all existing logic, supposed to be the least interesting body in the Kuiper Belt. The largest, yes, but size was supposed to correlate with boring in this context, not complexity. Instead, Pluto broke that equation, and it broke another one too. The size fallacy. Pluto forced a quiet reckoning with one of the core assumptions in planetary science. That size determines complexity. The conventional wisdom was clean and logical. Big worlds do interesting things. Small worlds cool off, freeze solid, and stop. Mars is bigger than Pluto, and it is geologically dead. The last major volcanic activity on Mars was somewhere around 100 million to 500 million years ago. Mercury is bigger than Pluto, and it is geologically dead. Its surface is essentially unchanged from the early solar system. Earth's own moon is bigger than Pluto, and it is geologically dead. The last significant lava flows on the lunar surface happened over 1 billion years ago. By the logic of size determines complexity, Pluto was supposed to be the most dead of all of them. The smallest, the coldest, the most remote. It had every reason to have shut down long ago. Instead, it turned out to be the one that is still actively reshaping itself, still building mountains, still flowing nitrogen glaciers, still turning over its nitrogen ice plains in slow convection cycles, more geologically alive, right now, today, than any of the larger rocky bodies in the inner solar system. Nobody has fully explained how a 2,377-kilometer wide ball of ice and rock receiving almost no solar energy, subject to none of the gravitational tidal forces that drive activity on the large icy moons of Jupiter and Saturn, manages to sustain the kind of geological activity that much larger worlds gave up on billions of years ago. The existing models of heat retention and radiogenic decay don't produce enough energy. Something else might be going on, and we don't know what it is yet. Right Mons, the impossible volcano. Right Mons changed the conversation entirely. It is a feature in the southern hemisphere of Pluto, roughly 150 kilometers across and about 4 kilometers tall, comparable in profile to some of the largest shield volcanoes in the solar system, though far smaller in absolute terms. At its summit, there is a central depression that looks disturbingly, compellingly, undeniably like a volcanic caldera. Not a random pit, not an impact crater with an unusual shape. A caldera, the kind of central collapse feature that forms when a volcano erupts and the underlying magma chamber empties and the summit collapses inward. When the New Horizons team first published the images, they were cautious. They called it a possible cryovolcano, a volcano that doesn't erupt with molten rock, because there is no molten rock on Pluto, but with a slurry of water ice, nitrogen ice, ammonia, and methane, driven by whatever internal pressure remains in Pluto's core. A volcano made of ice on a world made of ice, erupting into a sky made of ice. The caution was warranted. Claiming volcanic activity on a world this small and this cold, with the energy budget Pluto was supposed to have, was an extraordinary statement. And extraordinary statements need extraordinary evidence. The evidence kept arriving. The terrain surrounding Right Mons has almost no impact craters, which means it was resurfaced recently, geologically recently, meaning within the last 100 million years or so. The texture of the surrounding area is unlike anything else on Pluto's surface. Lumpy, hummocky, irregular, consistent with material that was extruded from below and then froze in place rapidly without time to flow very far. Nearby, a second feature called Picard Mons shows similar characteristics, though it's even larger, potentially one of the largest volcanoes, by volume, in the outer solar system. Together, they suggest that Pluto didn't just have geological activity in the distant past. It may have had eruptions, actual vomiting of material from below events, within the last few 100 million years. Some researchers believe the activity may have been more recent than that, though pinning down exact ages on Pluto's terrain is extremely difficult without surface samples. A study published in Nature Communications in 2022, analyzing the New Horizons data in detail, argued that the region around Right Mons was almost certainly shaped by recent cryovolcanic activity, and that the volume of material involved was substantial, enough to have significantly altered Pluto's surface chemistry. If you could somehow stand near Right Mons, and you couldn't, not without dying in seconds, but imagine it, you wouldn't see lava. You wouldn't feel heat. You'd be standing in near total darkness on terrain that crunches under your boots like packed snow, looking up at a mountain that once pushed ice up from kilometers below the surface into a sky so cold that the erupted material froze in place almost instantly, building a lumpy alien landscape of extruded ice that preserved the shape of its own catastrophic origin. A volcano made of ice. On a world that shouldn't have the energy to boil water, let alone push it through kilometers of frozen crust. It is one of the most alien landscapes we have ever documented anywhere in the solar system, and we found it on a rock most people forgot about after a naming dispute. The atmosphere that shouldn't exist. The atmosphere was another shock. Pluto has one. It shouldn't. Given its size, its gravity, about 6% of Earth's, and its temperature, the gas molecules that make up an atmosphere should have escaped into space long ago. The escape velocity on Pluto is so low that thermal energy alone should be enough to send atmospheric molecules flying off into the void. And yet, a thin envelope of nitrogen, methane, and carbon monoxide extends up to 1,800 kilometers above the surface. That's far higher relative to Pluto's size than Earth's atmosphere extends above ours. In absolute terms, Pluto's atmosphere is barely anything, but in relative terms, it is vast. New Horizons watched the sun set behind Pluto, a rare alignment that allowed scientists to use the spacecraft's instruments to probe the atmosphere in backlit detail, and saw the atmosphere light up in layer after layer of blue haze. The blue color comes from tholins, complex organic molecules formed when ultraviolet light from the sun breaks apart methane and nitrogen in the upper atmosphere, and the resulting fragments reassemble into larger, more complicated chains of carbon, hydrogen, nitrogen, and oxygen. These tholins are not benign or boring. They are among the most complex organic molecules naturally produced anywhere in the solar system outside of Earth and possibly Titan. The same class of molecules that, on the early Earth, may have been precursors to amino acids and nucleic acids, the building blocks of life. On Pluto, these molecules drift down from the upper atmosphere and settle onto the surface, coating everything in a reddish-brown stain. That distinctive ruddy color Pluto has in every photograph, that warm brownish tint that seems so incongruous on an object this cold, isn't rock. It's organic chemistry raining out of the sky. It's the residue of ultraviolet-driven photochemical reactions, slowly accumulating over millions of years. The breathing cycle. The atmosphere itself is unstable in a way that makes it even more fascinating. As Pluto moves along its 248-year orbit, its distance from the Sun changes significantly because the orbit is highly elliptical, more so than any planet in our solar system. At perihelion, its closest approach to the Sun, Pluto is about 29.7 astronomical units away. At aphelion, its farthest point, it is over 49 astronomical units away. That difference matters enormously. When Pluto is closer to the Sun, the surface nitrogen ice sublimates. It transitions directly from solid to gas without passing through liquid, and the atmosphere thickens. More gas, more pressure, more weather. When Pluto moves farther away, the reverse happens. The atmosphere freezes out. The nitrogen gas condenses back onto the surface as frost. The atmosphere collapses. Pluto is essentially breathing, inhaling its atmosphere, then exhaling it, on a cycle that takes nearly 2.5 centuries to complete. Scientists had predicted this cycle based on thermodynamic models. What they hadn't predicted was the complexity of what happens during it. New Horizons measured the atmospheric pressure at Pluto's surface at about 1 Pascal, roughly 100,000 times thinner than Earth's atmosphere at sea level. A pressure so low that by human standards it might as well be vacuum. And yet, within that almost nothing envelope of gas, New Horizons detected wind patterns, temperature variations with altitude, distinct haze layers stacked on top of each other like the rings of a tree. A world with barely any air at all had weather. The impossible dunes. What makes that weather even stranger is what it does to the surface. Pluto has dark streaks on its terrain that align with prevailing wind directions, the same way sand dunes on Earth align with wind patterns. In 2018, a team of researchers published findings in the journal Science, arguing that these features are wind-deposited ridges made of methane ice grains, dunes, on Pluto, built by winds blowing through an atmosphere 100,000 times thinner than ours. This shouldn't work. At that atmospheric pressure, the wind force is essentially zero by any standard we'd recognize. The grains should be immovable, and yet there they are. The mechanism turns out to be one that had never been observed or theorized before New Horizons saw it. The grains are lofted not by wind force alone, but by sublimation. As nitrogen ice turns to gas on the sunlit side of surface features, even the faint sunlight of Pluto is enough, given enough time. The escaping gas carries methane particles upward into the thin air. And the faint winds, though nearly powerless by terrestrial standards, are just strong enough to carry those lofted particles downwind until they settle, grain by grain, into ridges and ripples. It is an entirely new mechanism for dune formation, something never seen anywhere else in the solar system, something that shouldn't work by our prior understanding of atmospheric dynamics. And yet the dunes are there, photographed in detail, reproducible in simulations, confirmed by multiple independent research teams. Pluto keeps inventing new ways to be impossible. The subsurface. Ocean. Now take all of that, the convection, the mountains, the glaciers, the cryovolcanoes, the atmosphere, the dunes, the organic chemistry falling from the sky. Add it together, sit with it, and then add one more thing. Pluto may have a subsurface ocean. This is where it gets genuinely unsettling. Analysis of Sputnik. Planetia's position and Pluto's gravitational field has produced a series of observations that are difficult to explain without invoking liquid water beneath the surface. The basin is almost perfectly aligned with the tidal axis between Pluto and its largest moon, Charon, the line connecting the two bodies' centers of mass. In a tidally locked system, excess mass tends to migrate to this axis over time, the same way a spinning top will orient its heaviest part toward whatever is pulling on it. The fact that Sputnik Planitia sits almost exactly on this axis suggests it has excess mass relative to the surrounding terrain. One way to produce that excess mass, one of the most physically plausible ways, is a dense liquid layer sitting beneath the surface of the basin. Water is denser than ice. A liquid water layer under Sputnik Planitia would concentrate mass there and would naturally migrate to align with the tidal axis exactly as observed. A study published in 2019 proposed that this ocean might have existed since Pluto's formation, protected from freezing by a layer of gas hydrates, essentially a blanket of frozen gas molecules trapped in an ice crystal lattice, sitting between the liquid ocean and the outer surface ice shell. This insulating layer, perhaps tens of kilometers thick, would dramatically slow heat loss from the ocean to space, keeping liquid water stable for billions of years longer than the naive calculation would suggest. If that model is correct, Pluto has maintained a hidden ocean for nearly the entire history of the solar system. Longer than complex life has existed on Earth. Longer than the continents have held their current positions. Longer than the dinosaurs. Longer than the Cambrian explosion. Longer than most of the geological history of our own planet. If it's there, this ocean would exist in permanent darkness, insulated by a thick shell of ice, kept liquid not by the sun, which can barely warm Pluto's surface above the freezing point of nitrogen, let alone water, but by the faint, dying trickle of heat from Pluto's radioactive core. It would be one of the most isolated bodies of liquid water in the known solar system, a reservoir that has never seen sunlight, never been touched by solar wind, possibly never been disturbed by anything since it formed 4 billion years ago. That isolation is what makes the ocean scientifically electrifying to astrobiologists. We tend to think of life as requiring sunlight, warmth, a protective atmosphere, the comfortable mid-range conditions that define Earth's surface. But every decade, we discover organisms on our own planet that break those rules so completely that the rules seem, in retrospect, like failure of imagination. Microbes thriving in total darkness at hydrothermal vents 2,000 meters below the ocean surface. Bacteria living inside Antarctic ice sheets, metabolizing at temperatures that were supposed to be incompatible with biochemistry. Entire ecosystems in underground caves running entirely on chemical energy, with no sunlight anywhere in their energy chain. No photosynthesis, no connection to the surface at all. Organisms surviving in the crushing depths of subduction zones. Microbes living inside rocks deep in the Earth's crust, with generation times measured in thousands of years. If Pluto's ocean has a rocky floor, and models suggest it likely does, with the ocean sitting atop Pluto's rocky core, and if that floor is even slightly warmed by residual heat from the core, then you have the exact same basic ingredients that support chemosynthetic life in Earth's deepest oceans. Liquid water, mineral-rich rock, an energy gradient from warm to cold. Nobody is claiming there is life on Pluto. That would be an extraordinary claim far beyond what the current evidence can support. But the fact that we cannot rule it out, on Pluto, of all places, tells you how badly we misjudge this world. A decade ago, suggesting Pluto might have conditions relevant to the origin of life would have been a career-limiting move. It would have been treated as science fiction, not science. Now, it is a legitimate area of research, funded and published in peer-reviewed journals, taken seriously by serious people. Charon and the binary dance. Charon deserves its own mention because it complicates Pluto's story even further. Charon is enormous relative to Pluto. At roughly 1,212 kilometers in diameter, it is more than half Pluto's size. For comparison, Earth's moon is about 1/4 of Earth's diameter. The Moon-Earth system is unusual in our solar system for its size ratio. The Pluto-Charon system makes it look conventional. The two objects don't orbit the way the Moon orbits Earth, a smaller body circling a much larger one, with the center of gravity sitting well inside the larger body. Pluto and Charon orbit each other around a point in space called the barycenter, which sits between them in the empty space outside of Pluto's surface. The center of mass of the entire system is not inside either body. They are tidally locked to each other, face to face. Each one always shows the same hemisphere to the other. Pluto's Charon-facing side always looks at Charon. Charon's Pluto-facing side always looks at Pluto. They rotate in perfect synchrony, two worlds holding each other's gaze across a gap of roughly 19,600 kilometers, spinning together like two dancers locked face to face and slowly turning in a dark, empty ballroom, 5.9 billion kilometers from the nearest star worth caring about. Some scientists don't call Charon a moon at all. They call it a binary partner. The Pluto-Charon system, they argue, is more accurately described as a binary dwarf planet system than as a planet-moon system. This is not just semantics. The gravitational dynamics of the binary system are substantially different from those of a moon, and they affect everything else in the system, including the chaotic orbits of Pluto's 4 smaller moons. Charon's surface told its own dramatic story when New Horizons arrived. A massive canyon system stretching across its equator, some of the chasms running more than 5 times deeper than the Grand Canyon, hinting at a past where Charon's interior expanded as its subsurface ocean froze, splitting the crust open along stress fractures that circled the entire globe. And the northern pole. The northern pole was coated in a dark reddish cap, informally and with remarkable imagination, named Mordor Macula. The leading explanation is both elegant and strange. Methane gas escaping from Pluto's atmosphere drifts across the 19,600-kilometer gap to Charon, gets trapped at the cold polar region where temperatures drop even lower than Pluto's already extreme surface temperatures, and is then processed by ultraviolet light into the same tholins that paint Pluto red. Pluto is painting Charon with its own atmosphere. The two worlds are chemically connected across space, exchanging material, sharing chemistry, influencing each other's surface compositions, even as they drift endlessly around each other in the dark. The system includes 4 other tiny moons as well: Nix, Hydra, Kerberos, and Styx. All of them small, irregularly shaped, and tumbling chaotically through space in orbits that are destabilized by the gravitational complexity of the binary system. Their rotations aren't stable or predictable. They spin in ways that depend on which gravitational tugs happen to dominate at any given time. If you were somehow standing on the surface of Hydra, looking up at the sky, You would see Pluto and Charon circling each other in a slow, graceful gravitational waltz. And you would never see the sky look the same way twice, because your own world's rotation would be erratic, tumbling, never settling into a steady rhythm. The scale of the revision. What gets me, what I keep coming back to, is the scale of the revision. Before 2015, Pluto fit neatly into a simple narrative. Small, cold, dead, demoted. Every part of that narrative was wrong. It's small, yes, but it's running an active geology that rivals some bodies 10 times its mass. It's cold, but that cold drives processes we have never seen anywhere else in the solar system. Processes that required entirely new models to describe, new mechanisms we hadn't even theorized. And dead? Pluto is more geologically alive right now than Mercury, than the Moon, than Mars, than most of the rocky worlds we have studied up close across half a century of space exploration. The demotion almost certainly played a role in how long we ignored it. When the International Astronomical Union voted in 2006 to reclassify Pluto as a dwarf planet, public and institutional attention shifted away. Funding conversations moved to Mars, to Europa, to Titan. Pluto became a punchline, the planet that wasn't, the casualty of a definition debate. Alan Stern, the principal investigator of the New Horizons mission, never accepted the reclassification and has spent years arguing publicly that the definition used to exclude Pluto was poorly constructed and scientifically inconsistent. That a planet should be defined by its intrinsic properties, not by whether it has cleared its orbital neighborhood, a criterion that would exclude Earth from planetary status if it were placed in Pluto's orbit. Whether or not you find his argument persuasive, the data from his spacecraft made one thing unambiguous. Whatever you call Pluto, it is not boring, it is not simple, and it is absolutely, demonstrably, unquestionably not dead. The return mission. There is already serious discussion in the planetary science community about a return mission. An orbiter this time, something that could slow down, settle into orbit, and watch Pluto change over months and years rather than photographing it in a single frantic flyby. The concepts under discussion would represent a massive escalation in what we could learn. An orbiter could map the entire surface in high resolution, not just the hemisphere that happened to face New Horizons during the flyby. It could track atmospheric changes across multiple Plutonian seasons, decades by Earth standards. It could monitor the cryovolcanic regions for signs of ongoing activity. It could study the tidal interaction between Pluto and Charon in real time. One proposal, informally known by various names in different planning documents, envisions a nuclear-powered spacecraft carrying instruments specifically designed to measure the thickness of Pluto's ice shell using gravity mapping and seismological sensors, listening for the acoustic signature of the interior, trying to hear the difference between solid ice all the way down and a liquid ocean sitting beneath it. Such a mission could potentially confirm or definitively rule out the subsurface ocean hypothesis. None of these missions have been funded. The distances involved are staggering, and the travel time would be measured in decades, not years. A mission that launched in the 2030s might not reach Pluto until the 2050s or 2060s. In the current funding environment, where NASA's planetary science budget is perpetually stretched between competing priorities, a dedicated Pluto orbiter mission is a long shot. But consider what a single flyby revealed. Consider what 9 days of close observation, the duration of the New Horizons encounter data collection window, produced in terms of scientific revolutions: nitrogen glaciers, convecting ice plains, organic rain, mountains of frozen water standing like granite, ice volcanoes that erupted in total darkness, dunes built by winds that shouldn't be strong enough to move anything, an atmosphere that breathes on a 248-year cycle, and possibly, deep beneath all of it, an ocean that has been sitting in the dark since before anything was alive on Earth. All of that from a flyby, from one shot. Imagine what an orbiter would find. The pattern. We spent 76 years thinking Pluto was a planet, then 9 years arguing about whether it deserved the title, and exactly 0 years actually trying to understand what it was. The argument over the name was always a distraction. It was a procedural debate about taxonomic categories masquerading as a scientific controversy. Pluto doesn't care what we call it. It's out there right now, 5.9 billion kilometers away, doing things we can't explain on a time scale we can barely comprehend in a darkness we will never fully penetrate. But here's the most unsettling part. And, I mean genuinely, deeply unsettling, in the way that only scientific realizations can be. It's not any single discovery from Pluto that should keep you up at night. It's the pattern. Every time we have sent a spacecraft to something small and cold and far away, something we had confidently assumed would be boring, because it was small, because it was cold, because it was far, because the math said it should be dead, it turned out to be extraordinary. Enceladus, the tiny moon of Saturn that we assumed was just another frozen rock, turned out to be shooting enormous geysers of liquid water from its subsurface ocean into space, visible from orbit. Titan, Saturn's largest moon, turned out to have rivers, lakes, and seas of liquid methane, a complete hydrological cycle running on a different chemical than ours but operating on the same physical principles. Triton, Neptune's captured moon, turned out to have geysers of nitrogen erupting from its polar cap. Ceres, the largest object in the asteroid belt, turned out to have bright salt deposits suggesting recent geological activity and possible liquid water in its past. And now, Pluto, which was supposed to be the quintessential dead, frozen rock, which turned out to be running a geological circus. Every single one of these objects we assumed was boring until we looked. Every single one surprised us. Every single one forced a rewrite of the models. And how many objects like this have we not yet visited? How many Kuiper Belt worlds are sitting out there, beyond Neptune, in the dark, doing things we would never expect if we bothered to look? Thousands, potentially tens of thousands of objects, most of them completely uncharacterized. We have visited one of them up close. One. And it broke every assumption we had. The edge of the solar system isn't dead. The edge of the solar system is more alive than we ever imagined, and we've barely scratched it. Every icy body we haven't visited yet could be hiding the same kind of complexity. Could have its own Sputnik planitia, its own nitrogen glaciers, its own cryovolcanoes, its own organic chemistry raining from the sky, its own ocean sitting quietly in the dark, waiting. We don't know, because we haven't looked, because we decided, long before we had any real data, that looking wasn't worth the effort. Pluto is the proof that that decision was wrong. Every time, everywhere, for every cold, dark, distant thing we've dismissed without looking. The universe, it turns out, does not share our bias toward the convenient and the obvious. I hope you enjoyed the video. If you did, please leave a like. It helps the channel more than you might think. And if you want to see more videos like this, subscribe. There's a lot more out there in the dark, and I intend to keep looking.